Good afternoon, all. So this is week 5 microelectronics device to circuit problem solving session. So let's wait for 2-3 minutes. Then we will start the session. Okay, let's start the session. Am I audible? Hello.
Yes, ma'am.
Okay. So this is week 5 problem solving session of microelectronics device to circuit. And this is more details about me. So here we are going to solve some of the numericals and some of the MCQ question. So please try to solve this question. Question number 1, for a combinational logic gate alpha equal to 0.2, CL is the load capacitance 150 femtofarad and VDD is 2 volt, and there is a f clock equal to 2 gigahertz. So calculate the circuit power dissipations, and the second calculate the circuit power dissipation if VDD equal to 1.5 volt. So at first try to solve this question. So what is the right option here? At first, tell me how to calculate the power dissipation. What is the formula here, Manoj?
Ma'am, P is equal to CLVDD square into F, ma'am.
Uh, okay. Try with this equation. You can also recheck the equation. P equal to half of alpha into CL VDD square into F FCLK. Now calculate the power dissipation. Tell me when the VDD is equal to 2, in that case, what is the value of P? So using the dynamic power with the switching activity defined per 0 to 1 event. Okay. So P equal to half of alpha into CL VDD square into F. So if VDD equal to 2, first condition, VDD equal to 2. Tell me in that what is the value of this P? Half of alpha. Alpha value is 0.2, right? 0.2. What is the value of this CL? CL is 150 femtofarads. So 150 into 10 to the power minus 15. 10 to the power minus 15. Okay. Then VDD square. VDD square 2 square 4 into FCLK. It's 2 into 2 gigahertz. So if you convert from gigahertz to hertz, we have to multiply it with what? Hello? Tell me
Ma'am,
the conversion. Yes.
for which one, ma'am?
You just put the value of this FCLK, this 2 gigahertz
2
to
into 10
hertz.
power 9, ma'am. Gigahertz 10
Okay.
power 9.
Gigahertz to hertz. Yes, 10 to the power
10 power
9.
9.
Yes. Now tell me what is the value of this P in microwatt.
120, 120 microwatt, ma'am.
Yes, 120 microwatt.
Microwatt.
Now the same way you just have to find out the P value where the VDD is equal to 1.5. Now tell me the right answer. Microwatt. So if here I'm writing it, if the VDD equal to 1.8, oh sorry, 1.5, the second one, then tell me what is the value of this power dissipation. The P equal to half of alpha. Alpha is 0.2. Then CL, same CL value, 150.
67.5 microwatt, ma'am.
Yes, 67.5. So right option is option A. 150 into 10 to the power minus 15 into 1.5 whole square. VDD square into FCLK. FCLK is 2 gigahertz. That's 2 into 10 to the power 9. Now the value is 67.5 microwatt. So can I move forward the next question or any doubt?
Yes, ma'am. Next question.
Okay, so this is the question number two. In a CMOS inverter, short circuit power is consumed. First option during the changing and discharging of load capacitance. Second option due to the short circuit path between the supply rails during switching. Option C is due to the leaking diodes and transistor. And option D is the none of the above.
Option B, ma'am.
Yes, option B is the right option. Due to short circuit path between the supply rails during the switching. Good. So this is the question number three. Logical effort of a three input NAND gate is consider mu n equal to thrice of mu p. So calculate the logical effort. You have to find out the value of G. Tell me the equation. How to find out the for three input NAND gate. Three input NAND gate. Please try to calculate it. Three input NAND gate, the logical effort, and given is mu n equal to thrice of mu p. Hello. Tell me how to find out the logic gate. Sorry, logic effort.
Kindly explain from.
Okay. So in three input NAND gate, now three NMOS and three PMOS is in series. So thrice of NMOS NAND gate, like PMOS NAND gate. Next, I think I have put already 2 3 question. So there we will elaborate in details. Okay, just see how to calculate. For NAND gate, three MOS, NMOS and three PMOS is in series. So we have to count this value. So C input for three of NMOS, PMOS plus three. This is for NAND gate. NAND gate and thrice of three input. So three NMOS is participating and this both in series. NMOS. Okay, this is in series for NAND gate. Okay, and for and the it is for one PMOS for inverter. Okay, first one is for the NAND gate, and for NAND gate, uh, like three NMOS is participating and three PMOS is participating, and these both are in series. So thrice of in PMOS NAND gate for thrice of NMOS NAND gate by one for inverter. One of PMOS is participating for not, and one NMOS is participating. But here this is given. Okay, mu n equal to thrice of mu p. So we can say WP, the width, is equal to thrice of mu n. Sorry, Wn. Okay. So for inverter, this P here it is for the one PMOS. But here mu n equal to thrice of mu p. For W width, it is opposite. So WP equal to thrice of Wn. So one is multiplied with this three, like three PMOS. Why I am multiplying this? Because for NAND gate, three PMOS is participating. For NAND gate, three NMOS is participating, and both are in series. And for inverter, by the inverter, okay, one PMOS is participating and one NMOS is participating. But here is the condition that mu n equal to thrice of mu p for the inverter. Okay, so one PMOS is participating, but here is the condition thrice of mu p. So mu p is equal to thrice of mu Wn. That's why thrice of PMOS for not gate plus one NMOS for not. So tell me the value. 3 plus 3, 6 by 4, right? All is the NMOS, and this is for the N thrice 4. So the value is 3 by 2. Please go through this logic effort, how to calculate it. Okay, so the calculation part is that way, like 3 NMOS and 3 PMOS is in series, both are participating. Okay, but here is the by inverter. Like for inverter, one NMOS and one PMOS is participating, but here is the condition is given. That's why for NOT gate, thrice of PMOS, like for WP equal to thrice of mu n. Okay. From the next question, we can also clearly discuss. So can we move toward the next question?
Yes, ma'am.
So this is the question number 4. Calculate the delay for two input NAND gate which drives 10. Okay. And two input NAND gate as shown in the figure below, and consider the mu n equal to twice of mu p. This means when you are calculating for the like logic gate G, then it is for the NAND gate or NOR gate, whatever the given is, by the inverter. Okay. So for inverter, here is given mu n equal to twice of mu p. It means WP equal to the width of PMOS is equal to twice of width of WN. Okay. Now try to calculate. Then I will solve. At first, calculate the logic effort. Okay. G. Then try to calculate the F. At first try, then I will calculate it. I'm giving the hint. Calculate the delay. So you have to find out the total delay for two input NAND gate. Okay. Two input NAND gate which drives 10. So two input NAND gate are shown in the figure below. So you have to find out the value of at first F. Okay. So what is the formula for F? It is G into H. Then you have to find out the parasitic delay. So tell me what is the value of G here? How to calculate the value of G? Like H is given. This drives 10. Na? 10 is H. H is 10. Just see how I'm calculating. It will clear for you. So how to calculate this G? Like it is two input NAND gate, right? Two input NAND gate, it means two NMOS and two PMOS is participating. Okay. Two NMOS and two PMOS is participating. Okay, by inverter. Okay, for inverter, what happened? One NMOS and one PMOS is participating. For one NMOS, there is one, but for PMOS, what is the value? Like it is double of twice of like WN. So it is value 2. Okay, so now tell me what is the value of F? 2 plus 2 is 4, and this is 3 into 10. This is the way to calculate this F. Like 40 by 3. And please go through this chapter. How I'm calculating, what is this F, all these things. When you are calculating the delay for two input NAND gate. Two input NAND gate means two NMOS and two PMOS is in series. So 2 plus 2 and plus inverter. For inverter, one NMOS and one PMOS. But there is a condition that mu n equal to twice of mu p. So mu p is the opposite. Okay, twice of mu n. So one NMOS and this 2 is coming from that one. Okay, so F is coming, then calculate the parasitic delay. So this is the parasitic delay. Parasitic delay. What is the value of parasitic delay? N into P inverter, INV. So it's twice of into 1 equal to 2. This is the formula, but always remember, if it is 2 input, right, then the parasitic delay is 2. If it is 3 input NAND gate, then the parasitic delay is 3. Okay, 2 input, it's when the parasitic delay is 2. Now calculate the final delay. This is the formula, F into parasitic, F plus parasitic delay. Parasitic delay. Forty by 3 plus 2. So what is the value? 15.33.
15.33.
Yes, delay unit. So can I move toward the next question?
Yes,
This is the
ma'am.
way to calculate this, like the total delay. At first, we have to calculate the parasitic delay. Parasitic delay is if it is three input, then it is three. If it is two input, then it is two. Then how to calculate the f equal to g into h? How to calculate this logic effort? Logic effort is two input NAND gate. So two NMOS and two PMOS participating. Then just take this 2 plus 2 and by inverter. So one PMOS and one NMOS is participating. But there is a condition that mu n equal to twice of mu p. So one is for the NMOS and two is for the PMOS. If it is thrice of mu p, then it is thrice plus 3 plus 1. Okay. So just this is the way to calculate the total delay. So this is the next question. Question number 5. A 4 input NOR gate drives 7. So what is given here? 4 input NOR gate. It means the parasitic delay is 4, right? Drives 7. It's mean the age value. 7 is the age. And as shown in the figure, what is the delay in the driving for NOR gate? NOR gate is, see, this is in the parallel, in NOR gate, NOR gate, the NMOS and PMOS is in parallel condition. So only one is participating, not all these four. Okay. Before, for NAND gate, it is in series, but in NOR gate, it is in parallel condition. So any of it is participating. So now calculate it. And here is the condition like mu n equal to twice of mu p. Then it is means the WP is equal to twice of WN. Now tell me how to calculate it. See what is given here. And how to this G na, it is the logic effort. So logic effort is the like C in, this is the capacitance like C in by C inverter. This is the formula. So we just here calculate by the WN, the width. From the width and all the parameters are same. So C inverter. At first calculate the C inverter. C inverter, I have already to tell that this is the one NMOS and one PMOS is participating, right? Like the inverter, one NMOS and one PMOS is participating. So for NMOS it is WN and for PMOS it is twice of WP. So twice of WN plus twice plus WN. Okay, this is the inverter. And what is the value of C in? Now you have to find out the C in. I have already told that for NOR gate, 4 input NOR gate, the pull down network, okay, 4 NMOS in parallel. So only one acts in NMOS is enough. So four PMOS is in series. Just see the carefully. Hello, am I audible? Are you
Yes,
getting
ma'am.
my point? Like, how, like in the previous here also you can see how I have calculated this two. One is for NMOS and this two is coming from the PMOS. Okay, and for the inverter part, and upper is the NAND gate part. Two input NAND gate, so two NMOS plus two PMOS. Okay, and this is for one is for the NMOS and this two is coming from this part. Okay, two, and here I have written only the just forget this W and WP. Like in below part, C inverter, one is from the NMOS and this two is coming from here. So 1 plus 2, just see it. Okay, and for input part, it is for from the NOR gate. Okay, but in the NOR gate, only it is in parallel, like in NAND gate, it is in series, but in NOR gate, it is in parallel. So only like NMOS is participating or the PMOS is participating because NMOS and PMOS are in parallel. Okay, so here we are taking that the NMOS is enough. Okay, only the NMOS is participating because it is in parallel, so you can take anyone. So if the NMOS is participating, see, so four, like the four, four input, no, yes, four input NOR gate. So four PMOS is participating. I have taken the four PMOS is in series. Then WP bar, the final of WP is four input, so it is four, and it is twice of WN. Are you getting where this twice of WN I am taking? Is it clear? Tell me.
Yes, ma'am.
Well, tell me where I am taking this twice of WN. Like it is in parallel condition. Okay, NMOS or PMOS. Okay. So if it is the in we can take the only the PMOS is taking place or the PMOS is like it's in parallel, both sides are same. So here I'm we are assuming the four PMOS we are taking. So WP bar is equal to four inputs, so four multiply with this twice of WN, twice of WN, because this is the this part is given like mu n equal to twice of WP. So sorry, mu p, so it is WP is equal to twice of mu n. So it is 8 WN. Okay. So in capacitance per unit, the point is 4 NMOS in parallel. 4 NMOS in parallel. So only one active NMOS is enough. Okay. So one NMOS is participating and 4 PMOS is participating. So input capacitance per unit. After the session, please practice this. Input capacitance, because this type of question is going to come in your exam. So input capacitance per unit, and please go through the lecture. This is the most important lecture, I think. 1 NMOS, 1 NMOS plus 1 PMOS. This is the 1 PMOS. Okay, 1 PMOS. So I'm writing here. So for NMOS it is WN, and it is 8 PMOS per unit. This is 8 WN. So total is 9 wn, because only this NMOS is in series for NOR gate, so only one NMOS is participating and 4 PMOS. So it is 4 input and 4 input and twice of N. So it is 8 N. So total is 9 W by N. So C input equal to 9. Here it is 9. So 9 by 3. So G is equal to 3. Here the logic effort equal to 3. Okay. So next I'm writing here. So G we have calculated. Now the load capacitance, L load equal to, it's the like F equal to G into H, right? Here you can see the F equal to G into H. Just multiply the load capacitance. If G into H, just 9 into H value is 7 is identical gate. Gate drive 7, so H is 7. So it is 63 WN. Or you can take only the 63 the value, okay? Now the
Ma'am, G value is 3, ma'am.
yes.
G value is 3, ma'am.
Okay,
You have
sorry.
written 9.
Yes, the G value is 3. Sorry, this is the C load. Sorry, this is not the logical effort. Just a minute. Here is a little mistake. This is the load capacitance. Sorry, the load capacitance. Load CL. This is CL, not this G into H. Sorry, by mistake. So this is the CL. The final value we have to find out the CL by C inverter. Okay. So C load equal to 9 into 7, because 9 we are getting from the here. Okay. And this 7 is total, the gate drive 7 identical gate. So this is the C load, the load capacitance. 9 into 7. Then find out the the electrical effort. So electrical effort is, first we have calculated the logical effort, then we have calculated the C load. C load is equal to this total capacitance multiplied with this 7. This NOR gate drives the 7. So multiply with the 7. Then the electrical effort. H. You have to find out the value of H. C load by C in. CL, C load by C inverter. So this is equal to 7. Like here it is given the it drives 7, so it's totally have taken from here the 7. Then P inverter equal to 4. Like it is 4 input, so the parasitic capacitance is 4. Okay, then just find out the total delay. The total delay equal to G into H plus parasitic capacitance. So G into H, G is equal to 3, H is equal to 7 plus 4, the parasitic capacitance. What is the value of it? Tell me. 25, right? Is it clear?
Yes, ma'am.
Okay. So this is the question number 6. What is the function of the passivation layer in IC fabrication? Provides the mechanical strength. Option B is the protect the active device from the environment. Option C reduces the capacitance, and option D is increases the carrier mobility. Please practice at least 4 to 5 question practice on the total delay of this NAND gate, NOR gate, this type of things. Okay. So this is the question number 6. What is the function of the passivation layer in IC fabrication?
To protect active device from the environment.
Yes, option B is the right option. So next question number 7. In CMOS technology, NMOS and PMOS devices are fabricated on same metal layer, different metal layer on same substrate on different substrate.
Same substrate, ma'am.
Yes. So option C is the right option. Then question number 8. Clock gating is used for reducing the dynamic power consumption, reducing the transistor count, increasing the clock frequency, or decreases the clock frequency.
A option, ma'am. Reducing dynamic.
Reducing the dynamic power consumption. Good. The question number 9. In the twin-up process of CMOS fabrication, following steps are employed. First option is the gate and field oxide formation. Second is the metallization. Then third, N-well and P-well formation. And fourth is source and drain implantations. So find out the correct way to deposit or fabricate this CMOS using the twin-up process.
Ma'am, fourth option.
Can you little bit explain?
Ma'am, the fourth option is correct, ma'am. I didn't know correctly, ma'am.
To like make the N-well and P-well formation. Okay, then we have to prepare the gate and field oxide formation, and after that source and drain implantation is happening, and final stage is the metallization. So option D is the right answer. Next question number 10. In CMOS technology, shallow P-well and N-well regions can be formed using low energy sputtering, low pressure chemical vapor deposition, low energy ion implantation, or low temperature dry oxidation.
Ma'am, third option.
Low energy ion implantations. Question number 10 is yes, option C is the right option. So CMOS technology, shallow P well and N well regions can be formed using the low energy ion implantations. Good. The question number 11, energy in a CMOS inverter during 0 to 1 output transitions is proportional to input capacitance, load capacitance, propagation delay, or threshold voltage.
Load capacitance, ma'am.
Yes, load capacitance is the right option. Option B. This is the question number 12. In CMOS circuit, dynamic power dissipation is mainly due to leakage current, charging and discharging of load capacitance, subthreshold conduction, or gate tunneling.
Ma'am, maybe it's option B.
Yes, option B is the right option. Charging and discharging of a load capacitances. There is a question number 13. For a CMOS circuit, VDD is 1.8 volt, ISC is 2 microamps, switching probability is 0.5. So find the short circuit power dissipations.
Ma'am, 1.8 microwatt.
Yes, 1.8 micro. Tell me how to calculate it.
Ma'am, short circuit power dissipation is equal to
Mm, yes,
VDD into ISC into P01.
yes. The switching probability. The VDD into ISC into switching probability P01. So put all the value like 1.8 volt. What is the value of this ISC? It is 2 microamps into 10 to the power minus 6 into 0.5. So what is the value? It is 1.8 microwatt. Okay. So next move towards the question number 14. A CMOS logic gate dynamic power is 4 microwatt and propagation delay is 200 picosecond. So find out the power delay product. So how to calculate this power delay product?
Dynamic power into propagation delay.
Yes, dynamic power into propagation delay. Tell me the value. So PDP is equal to this dynamic power into propagation delay. Good. Tau P. Okay. So tell me the value. 4 into 10 to the power minus 6 watt into 200 picosecond. Zero 0.8 femtojoule. Tell me I'm right or
Yes, ma'am. 0.8 Fermi, ma'am.
if joule. So can I move toward the next question?
Yes, ma'am.
So this is the question number 15. The concept of logical effort is primarily used to minimize the power dissipation, minimize the delay in logic circuit, or reduce area overload, or increase the noise margin.
Option B, ma'am.
Yes, the minimize the delay in logic circuit. This is the question number 16. A fan out of 4 inverter delay is to be calculated for a 180 nanometer technology. Okay. This is the technology 180 nanometer technology. G equal to is given, H equal to given, P is given, and tau is also given. So how to calculate the delay? Have you all? We have already solved. Na delay is equal to G into H into P. And the total delay, how to calculate? Just multiply with this tau.
5, ma'am. Total delay.
So this value is 5, right? Uh, Sorry, what is the value of this D? 5. Yes, 5. And the total delay is like tau is equal to picosecond. So just D into tau. So D is 5 and multiply with this tau. It is 12 picosecond. So total delay is 60 picosecond. So similar type of question, please at least try 4 to 5 similar type of question you have to practice. So this is the question number 17. The parasitic delay of an n input NAND gate is approximately. Tell me what is the right answer. I have already
N,
told.
ma'am.
Yes, n input, it means the parasitic delay also n, right? N input, it means the parasitic delay is also n. Which step is fabrication is responsible for defining the minimum feature size, channel length in MOSFET? Diffusion, oxidation, photolithography, or metallization?
Option C, ma'am. Photolithography.
Yes, photolithography. Ion implantation offered better control of doping profiles compared to diffusion because it requires lower temperature, it allows the multiple energy implants for precise profiles, and option C, it avoids the crystal damage completely, or option D, it eliminates the need for annealing.
Ma'am, option B, ma'am.
Yes, option B is the right option. It allows the multiple energy implants for precise profile. This is the question number 20. In CMOS fabrication, what is the purpose of N-well and in a P-type substrate? To form a PMOS transistor, to reduce the leakage current, to isolate the device, or to increase the mobility? In P-type substrate, why the N-well is, what is the need of this N-well? You have seen the like NMOS or PMOS. Like if it is a P-type substrate, no, then this is called, we can here form the NMOS. Like there is a N plus plus something is doping there, but there is a gate and the metal the gate oxide and like CMOS. In CMOS, this is the A, like NMOS. P-type substrate, it has been the NMOS. But we need the N-well. This means we are here, N-well is doping. Like here we are preparing the N-well. It means it acts as a N type of substrate. And then we are doing the doping or something implantation and we are forming something. So it is act as a P-type substrate and N-well means it acts as a same substrate, but it is acts as a N type of substrate. So NMOS and there is a PMOS. So it's prepared the CMOS. Okay. NMOS and PMOS both in the same substrate. It is making the CMOS. So what is the need of this N-well? To form the PMOS transistor. Is it clear?
Yes, ma'am.
Yes. So next, the etching process in IC fabrication can be performed by only wet chemical etching, only dry plasma, either wet or dry, or none of the above.
Option C, ma'am.
Yes, option C. Either wet or dry, both. The question number 22. A silicon wafer is oxidized 1000 degree to grow the 500 nanometer of SiO2. If the growth rate is 50 nanometer per minute, how long does the oxidation takes? How to calculate? In 1 minute, it is 50 nanometer. So you have to grow the 500 nanometer. Tell me how to calculate.
Ma'am, thickness by growth rate.
Yes, thickness by growth rate. So what is the right answer?
10 minutes, ma'am.
Yes, 10 minutes. 500 by 50. So it's needs 10 minutes. Next question. Suppose N-well is formed using the diffusion at 1000 degrees centigrade. The diffusion coefficient is given for a diffusion time is 1 hour. So estimate the junction depth. So what is the equation? How to calculate the junction depth? Xj. Tell me the formula.
Ma'am, Xj is directly proportional to root of D, ma'am.
Yes, so xj equal to root of d into t. Okay, t is the time and it is in second. So now calculate what is the value of this d.
Ma'am, whether Xj should be in centimeters, ma'am.
Yes, it is in centimeter. D is in centimeter. Okay, so you have to find out in centimeter, or you can convert it into the micrometer also. And what about the t? It is in second. So 3600 second. So tell me the answer.
Ma'am, X is equal to 0.268 micrometer.
Yes, 0.26
268.
micrometer. Yes, this is the right answer. So next is the which aging process offer the base anisotropy. Anisotropy means directional. Isotropic in aging in both direction, but anisotropy means the in a particular direction. So wet chemical, plasma dry, or buffered oxide etching or isotropic etching.
Ma'am, option B.
Yes, option B. Dry etching is anisotropic. So why ion implantation followed by the annealing? To change the dopant polarity, to repair the lattice damage and activate the dopants, to reduce the wafer thickness or to increase the diffusion coefficient.
Ma'am, option B, to repair lattice damage and activate dopamine.
Yes. Option B is the right option. This is the question number 26. The minimum feature size that can be transferred in a photolithography depends on oxidation rate and resist thickness, wavelength of light, and numerical apertures. And option C is the type of dopant used, and option D is the wafer diameter.
Ma'am, option B.
Yes, option B. wavelength of light and numerical apertures. So question number 27, the native oxide thickness of a silicon in room condition is typically less than 2 nanometer or equal to 10 nanometer or 100 nanometer or greater than 1 micrometer.
Less than 2 nanometer.
Yes, less than 2 nanometer. This is the question number 28. In a photolithography system, uses light of wavelength lambda equal to 365 nanometer and lens in a numerical aperture is 0.5. So estimate the minimum feature size or resolution possible. So you have to find out the L minimum. Tell me what is the equation? How to find out the L minimum? Zero point 0.61 into lambda by, tell me the equations, by Na. This is the equation. Now tell me what is the value of this L minimum? 0.61 into lambda by Na.
445.3 nanometer.
Yes, 445 nanometer. So this is the question. A boron diffusion process is carried out at 1000 degrees centigrade for 1 hour. If diffusion coefficient is 1.5 into 10 to the power minus 14 centimeters square per second, estimate the junction depth. Already we have calculated. So tell me how to calculate the junction depth, xj. What is the equation? Root over dt, right? T value is given 1 hour. It means 3600 3600. And what is the value of this d? 1.5 into 10 to the power minus 14. Now tell me the answer, xj.
I'm 7.3 micrometer.
It is 7.3 or 0.073 micrometer. Just calculate this point.
I have
It
got
isn't
73 into 10 power minus 7. Ma'am.
7.3 into 10 to the power minus 6 centimeter.
7.3. Oh, okay, ma'am. I have not considered 1 minute. Ma'am. Yes, ma'am. That means 7.3 10 power minus 6 centimeter, I think. Ma'am.
Yes, just 7.3 into 10 to the power minus 6 centimeter. So if you convert in micrometer, it is in 0.073 micrometer. So can I move towards the last question?
Yes, ma'am.
Yes, so this is the last question of today's class. So here, this is the simple question. A wafer undergoes a metallization with aluminum. The resistivity is given. So if interconnect length is 500 micro, width is also given, thickness given. So find out the resistance. Simple, put the formula. You have to find out the R and the rho is given. And tell me the value of R.
Ma'am, 2.7K ohms.
Just put the value. Just see the
2,
calculation.
2.7K, ma'am.
R equal to rho L by A, right? So what is the value of this rho? It is 2.7 into 10 to the power minus 6 into L. What is the value of this L? L is the micrometer. Okay, and this is in centimeter. So 500 into, just convert it to meter. Four micrometer. It is meant 10 to the power minus 6, but it is in meter to centimeter, I think. Just convert it. And rho L by A. A is width into this one. So 1 into 0.5 into 10 to the power minus 8. Now tell me the answer.
27 ohms, ma'am.
Yes, 27 ohms. Okay, so this is the last question. Next we'll meet next Tuesday 7 to 9 p.m. You can leave.
Thank you,
And
ma'am.
please practice this type of question, okay? And go through the lecture which already shared in the class.
Thank you, ma'am.
Okay.